Okay guys, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi. Have a very good day. Sorry for the delay. Okay, we shall use the slide that provided by Dr. Sharah Shikin directly because frankly to say, your next coming task will be handled or will be produced by Dr. Shikin. So we shall refer to her slide directly and we shall discuss accordingly. Okay, our topic now is on the DC-DC DC-DC converter and preferably the buck converter for part 1. Okay, throughout the slide and the topics of this DC-DC converter, we shall go through the introduction on the preference or on the introduction of the DC converter, and we shall go through the introduction on the linear regulator, the regulator that being used primarily in terms of how to regulate in terms of DC into DC, certain level into certain level. So how the converter is controlled, and we go to the recent development or approach of the DC-DC converter mode, which is on the switch or switch mode regulator concept. Okay, on the introduction, the DC converter is used to convert in terms of unregulated DC input into a controlled DC output at a desired voltage level. And the converter for sure can be used to step down or step up. And so we have a DC input, certain DC input, but we need certain DC output at certain level. So we might have to step up or step down. So this is the ways or the purpose of DC-DC converter. So we are talking now about the DC or the power processor and how we want to process or convert higher or lower based on what source we have, based on required load source needed from the source. Okay, this the converter can be used in terms of to control automobiles voltage levels, traction motor. So also be used in regenerative braking for DC regulators. So when we put in or we include the inductor, so we can generate DC current source and convert DC voltage into DC current. So we can integrate also in the energy conversion system in terms of renewable energy conversion technology. So the DC converter can be used to step up or step down based on requirement or preferred levels of the grid. Okay guys, again to repeat in terms of visualization diagram. So let's say we have a power converter or power processor to convert DC to DC. So we have a source here and we have a load here. So we have certain level of source voltage and the required load may be lower or higher. So this is the purpose or the function of this power processor here, to maintain the output at certain higher level regardless anything happen to the load to the source. Let's say the source have a ramping down voltage, so the load must be maintained at higher voltage. Let's say maybe the source is fluctuating higher and lower, we're getting higher. Let's say we have a source of PV panels. So when the intensity of the sun is high, so your power or your voltage will increase. But when intensity reduce, so the voltage will reduce. So it fluctuates between high and low. But the main things that we have to take care is that the power processor should be able to maintain the output voltage either at higher or low voltage. So let's say we have a grid as a load, so 400 volt as our voltage level. We have a stereo, maybe 13 volt. We have a LED load, so 5 volt. So this is the variant of voltage output that required by the load. Meanwhile, our incoming will be fluctuate higher or lower based on intensity of the sun. Okay. Okay, we refer back to the slide. Actually, for DC-DC converter, we can categorize or group as a non-isolated or isolated kind of converter. For a non-isolated converter, it is a simple electrical conversion circuit to convert between what we have as input and what we call it as output. So amongst this kind of non-isolated converter, we can categorize as a linear regulator, switch mode regulator, such as for buck boost or buck boost, chuck and static converter, and some more, which is the input and the output is not electrically isolated. So, but when we refer to the electrically isolated converter, we are referring to the converter that use transformer in between your input and output circuit or conversion circuit, such as for flyback, forward, push-pull, full bridge converter, half bridge converter. So we shall take a look on the diagram itself. So from the schematic or the circuit diagram, we can differentiate between an isolated kind of and non-isolated kind of converter. For the time being, if we refer to the earlier kind or type of converter, which is linear regulator, so we take a look in the visualize mode. So you may write and sketch based on what we have discussed here. You may stop or you may pause and you may rewind again, replay again this slide for your own convenience. So for the linear regulator, we shall convert in terms of unregulated DC input into a controllable DC output at the desired voltage level. So let's say we have here our input source, we have here the load. So we have here certain level of voltage we need. So for a linear regulator, we only can able to step down in terms of conversion. We are able to step down only because we have source of E and we need V out. So this is E in, V out. So this linear regulator in the earlier age is just like a simple voltage divider. We have here R variable. So if you probe here and the voltage that you measure out at this level, this is ground. So if you shift this voltage probe higher, so V out will be higher. If you shift lower, so the V out will be lower. So it's just like a voltage divider rules concept. And you probe the output here. You shift upper or lower, so the V out shall vary based on the resistance that appear on the probe. So V is equal to IR. V is equal to IR. So the I is the same across the circuit, but the R is depend on the probe that you put in. You put in higher on the circuit, so the voltage, the resistance will be higher. So the voltage will be higher. If you put at lower, near to the ground, so the resistance will be lower, so the output will be lower as well. So it just follows the voltage divider rules for the linear regulator. But the problem is that even though you are not connecting to the load, so this is your load, you probe at certain point, you connect to the load, so both are grounded. So what happens is that if you take out the load, still there is a current that flows from positive to the ground terminal, positive to negative terminal, means that there is a losses. And these losses, if compared to the current that delivered to the load, so you can refer to the graph. If you probe at the highest point, means that you probe at the highest point here, so all the voltage will go to the load. So all the voltage and the current will go to the load. So the efficiency V out divided by I E in is that the voltage output compared to the input voltage. So the efficiency is 1. So it adds highest efficiency. But if you reduce or you slide down the probe lower, means that maybe half of the point, 50-50. So this is the point, and you shall have the V out of 50% of the input. Your V out is 50%, so means that 0.5 here. But in terms of losses, so you can see that the losses curve here. At 50%, the losses is the highest peak. At 100% of output, so it reduces to 0. At 0, so 0. But at 50%, you slide at 50% of the resistance, so you shall have a 50% of efficiency of the system. So these losses, where it convert to, so it convert into heat, and convert into heat. So P losses will become heat, and you will heat. The heat has to be dissipated by the regulator. So that's why when you take a look at the linear regulator, usually we have a 3-pin regulator, LM whatsoever. So we have your metal tab. So this metal tab should be attached to the heatsink. We shall take a look further in the consideration of this heatsink or the power dissipation issues on the final chapter that we shall discuss in this topic or this subject. Okay, this is the inconvenience or the lack of the linear regulator parts or linear regulator circuit. So that's why for this linear regulation kind of concept is only used for tabletop power device. Means that maybe a few milliamps or few watts. But if you go to tens or hundreds of watts, the linear regulation concept is not going to be used. Okay. Another linear regulation approach, instead of use variable resistor, just now explained, we usually use BJT, bipolar junction transistor. Means that when we induce current at the base, so we shall modify or we shall able to limit the amount of current that flow through the circuit, and also the voltage that being blocked or being released to the circuit. So this is the curve. Means that at certain current, so this BJT is controlled by current, means that maybe we have certain level of current, we need to full open the circuit at certain amount of current, maybe 10 milliamp, but when we apply maybe 5 milliamp, so the amount of voltage that emit at the emitter, so this is the collector, emitter, base, maybe just release half of the voltage that it should release from the source. So let's say we have I in of 100 volt. So the source or the load only receive 50 volt when we put 5 milliampere. Maybe we adjust at 3 milliampere, so it will be only 30 volt like that. If we put 10 milliampere, so it will release full voltage to the load of 100 volt. So like that. Just same like the sliding concept of your rheostat just now. Okay, but this one is controlled by BJT. But the problem is that the losses occurred here when we have a voltage drop through your transistor times the I collector. So this is the losses that happened to the circuit. So this is the